So in the last lesson, we looked at how to take a very smooth sine curve with lots of different unique y values and turn it into a more rationalized representation of the sine curve using however many unique values we wanted. In this case, I'm showing a sine curve displayed with only 6 y values. Now what we want to do is use this same concept to displace lots of panels on the surface of a facade. So we're going to use quite a few of the components of our previous script from the last exercise. But first, let's build our grid of panels in a new definition. We're going to do this using the rectangular grid component, where we can set the dimensions of each grid cell. So let's just make that horizontally 3.5 meters. On the X and 3 meters on the Y. And let's set the number of horizontal modules or horizontal cells on the X value is 10, and on the Y value corresponding to the number of floors, let's say 50. So that would be our elevation. Now we want to somehow feed information for each of these panels or rectangles as X values into our previous script's graph mapper function. So let's just copy this part of our previous script and place it here. Now last time we simply created a series of numbers which would correspond to X values. But we're not going to do that this time. We're going to feed it some different information. First, however, let's just go back and look at the data structure here. It's actually organizing it into groups of columns. So 10 columns with 50 panels each. And for reasons which will become clear later, we want to switch this around and organize it into groups by rows instead of columns. We can do that by flipping the matrix. And that gives us branches by row. So 50 branches with 10 items each. Now let's just take each of these rectangles and find its center point using the polygon center component. So that's going to give us the point at the center of each of these panels. Now what we want to do in order to get our X values and create this curve is actually use the concept of an attractor to relate the sine curve that's going to ripple through the surface, to relate that curve to a geometry that we draw and control. It's going to be a line in this case. So we'll just draw a line and measure the distance of each of these points to the closest point on this line. So that's going to create the effect of a sine wave that expands outwards from this line, or it'll look like a diagonal wave on this surface. So let's just put this curve into Grasshopper. and find the nearest distance to this curve from each of these points. That's going to be our y value. I mean our x value, sorry. So we'll connect this here. And we should get a set of y values. However, there's one important thing. If you remember, when you remap numbers, you need to get the set of bounds. What's happening here, however, is that because there's a data structure, it's not getting one single domain for the entire set of values. It's actually getting one unique domain for each row, which is no good. So what you want to do is flatten this end. It's really important that it's this end and not this end of the bounds component, and you come away with only one domain. So that's going to give you our set of y values. Now we can just copy most of the rest of this definition, because it still applies. These horizontal markers aren't really useful for us anymore. Let's just copy that. And paste it in here. Now we have our remap values here again, and again we have to flatten this end. Otherwise we're getting loads of different domains for each row. That works. And now instead of using this to plot a point like we did last time, we're going to use the resulting displacement values to define a vector in the z direction, because that would be the panels being displaced forward from the facade, which is what we want. And then just take each of these cells. I'll be sure to use the ones that come from the flipped version of this list, because otherwise it won't match with what comes later. So we'll just want to transform all of these by their corresponding vector in the z direction. And that should bring them forward. Now we can just take them and create surfaces. And in order to create the size of these extruding boxes from the facade, we can just create an extrusion with using the same curves. And the same vector. Now some of these are invalid because some of the closest ones to the facade are only being extruded by 0, so they're not being created, but that's okay. So let's just hide everything that is not the result. Now, what you're noticing is that for a facade, these are coming out quite far. And that's because we've set our multiplier here, which effectively is the maximum amplitude, at 10. So we should try 3 meters as the maximum extension. That seems a bit more reasonable. And we can play around with this graph mapper. And create the relationship that we want. Oh, but actually, if you look at the surface, it's not doing exactly what we want. It's not creating waves that are parallel to this line. There's something that we haven't really plugged in correctly at some point along the way. And actually, it's right here. We connected the points output of the closest distance to a curve component instead of the distance output, which is what we wanted. That should go here. And that should also go here. Right. Now, see, this sine curve is always defined as the distance of each point perpendicular to this line. So if this is a bit difficult to read, we can also display it a bit differently. We can create a custom preview component, plug the geometry in, and create a color swatch. And just display a color that we find easier to look at. Okay, so the next exercise is going to be about visualizing each individual module here colored according to its indices. So we can start looking at how these modules are working throughout the surface and whether they're doing what they're supposed to or whether they're not optimized.